Okay, let's get started for. Okay, let's get started for the third lecture of Francesco.
Can you hear me? Yes. Can you hear me? Yes. Okay. So today I would like to discuss gauge theories with fermions. And so before doing that, I would like to say a few things about the fermion path integral in 2+1. So today I would like to discuss gauge theories with fermions. And so before doing that, I would like So let's try to study a free Dirac gauge field and also some metric, background field, gauge field, and also some metric. And so the Lagrangian for this theory is very simple. It's just the free Dirac. And so the Lagrangian for this theory is very simple. It's just the free Dirac Lagrangian. So we want to compute the path integral of this theory. And so we consider as Lagrangian. So we want to compute the path integral of this theory. And so we consider as an Euclidean oriented three-manifold, and then the partition function is just given by the determinant of the Dirac operator. An Euclidean oriented three-manifold, and then the partition function is just given by the determinant of the Dirac operator. It's a function of the background. So at least formally is given by this determinant, which is a function of the background. So at least formally is given by this determinant, which is the product of the eigenvalues. Now, this is, so the Dirac operator is Hermitian of the eigenvalues. Now, this is, so the Dirac operator is Hermitian, and so these eigenvalues are real. And in fact, a free Dirac fermion is a theory which is parity, and so these eigenvalues are real. And in fact, a free Dirac fermion is a theory which is parity invariant, time reversal invariant, also charge conjugate invariant. And since in the Euclidean signature, if we reverse the orientation, time reversal invariant, also charge conjugate invariant. And since in the Euclidean signature, if we reverse the orientation of the manifold, we get a complex conjugate partition function. For this theory, the partition function should be real. And in fact, at least formally, with manifold, we get a product of real eigenvalues, and so these objects should be real. Now, there is no problem in giving a good definition for the absolute value of the partition function. So going from the formal definition to an actual number, this is just the product of the absolute values of all these eigenvalues. This can be defined with zeta function regularization, of Pauli-Vilas regularization. So there is no problem with this. However, there is a problem in defining the sign. So we take a gauge transformation, let me call it phi, and we transform it to some other connection and, some other metric, so some gauge transformation, some diffeomorphism. And then we consider an interpolation between the two. So we consider a class of AS, GS. So for instance, AS is just given by 1 minus S A0 plus S A1 with S that goes from 0 to 1. And we do a similar thing with the metric. So when S is equal to 0, this is just equal to A0. When S is equal to 1, is equal to A1. And in the middle, it interpolates between the two. Now, of course, so the beginning and the end, they are related by a gauge transformation. But in the middle, this is not a gauge transformation. It's just some continuous, smooth deformation of this bundle that goes from here to there. Well, of this connection, it goes from there to there. And we do a similar thing with the metric. Okay, so now, okay, we compute the spectrum of the Dirac operator on this on the manifold that we are looking at with this bundle, and okay, let me plot an hypothetical result. So we start at 0, and there will be some spectrum for these eigenvalues. Now at 1, this is just a gauge transformation. This is at 0, this is at 1. This is just a gauge transformation, and the spectrum of the Dirac operator is gauge invariant, so we're going to get the same spectrum. Okay, and then as we vary, as we go with this interpolation, instead this is not a gauge transformation, so the spectrum will change, and it has to go back to itself. However, the individual eigenvalues, they do not have to go back to themselves. It's just the spectrum which is the same. And in fact, in general, there is a phenomenon that we can call spectral flow. Okay? So it might happen that these eigenvalues goes here, this goes here, here, and so on. Okay? It's just the spectrum which is the same. And in particular, it might happen that in this evolution, there is some eigenvalue that from, for instance, in this case, from negative goes positive. Okay? And so if we construct this function, this hypothetical function, which is the regularization of this expression, such that it is continuous, it is clear that it has to change sign when one of the eigenvalues changes sign. And so in this situation, we would find the result that the partition function at A0, G0 is equal to minus the partition function of A1, G1. And so in particular, it cannot be gauge invariant, right? Because it's the same, well, it is a gauge transformation, but it has picked a minus sign. Now, in fact, one can use an index theorem to understand when this happens, and this does happen if you take suitable manifolds with suitable bundles. So this is a problem. And it shows us that there is a problem in defining this partition function if we insist that it is both real and gauge invariant. So what do? Well, we do not want to give up gauge invariance because we want to construct gauge theories, and so we give up parity. Now, let me stress that this does not mean that the theory of a free fermion is not parity invariant. It is parity invariant. The problem is when we couple to a background. So as long as this is just a background, the theory is parity invariant and time reversal invariant. The problem comes if, well, either if we turn on the background, and then the background breaks this invariance, and in particular, if we make this background a dynamical field, then in that theory, parity is broken, okay? It's just a phase, yeah, well, it's just a sign, actually. So here I'm trying to insist that it is real, and I saw a clash between reality and gauge invariance. So now we have to do something, and okay, I will tell you in a second what we can do. So we give up parity, and in particular, we give up the fact that this regularization is real, okay? And so, so we can construct a gauge invariant partition function, but only if we make it complex, and so if we introduce a suitable phase. And this phase, what is it? Well, essentially, it's the regularization of this infinite product of signs. And so what we can construct is the following object. So as we said, there is no problem with the absolute value. But we put a phase, so let me write it, and then I will explain. So minus I pi over 2, and some object, eta, it depends on the background. And what this eta is the regularized, so in fact, we could choose different regularization. We want just to regularize this infinite sum of signs. And so, for instance, we could take the following. So let me first write it. So it's the limit, epsilon to 0, plus sum over k, sine lambda k, e to the minus epsilon lambda k squared. So if we formally take epsilon equal to 0, this is not there, and this is either plus 1 or minus 1, and so put here, it means that it gives us either minus I or plus I. So it gives us opposite sign, and something with opposite sign according to the sign of lambda k, but now we regularize this object with this thing, we take the limit and we get some well-defined object, which however, is a generic phase. Okay, so this object is not equal to plus or minus 1. This is a generic phase. And this object here is called the eta invariant. And since this object is constructed uniquely with the spectrum, right, the only thing that goes into this definition is the spectrum, and the spectrum is gauge invariant, this object is gauge invariant. However, as we said, this is a generic phase. So this partition function we obtain, which is gauge invariant, is no longer real, okay? It's complex. Is it clear? Any question? Okay. So what is this object here? Well, the Atiyah-Patodi-Singer index theorem tells us the following, that if we take e to the minus I pi eta, we can express this quantity in terms of Chern-Simons terms. So let's see, minus I Chern-Simons A minus, let me write this way, I 2 Chern-Simons graph. Okay? So this is 1 unit of Chern-Simons term. I mean, a Chern-Simons term at level 1. So this would be integral A dA in 3-dimensional terms. And this is the gravitational Chern-Simons term that we wrote yesterday. Okay? Yes? No, they are not. We are in 3 dimensions. So they are not, you see, there is no symmetry that maps an eigenvalue to minus itself. If you want parity, it would map, I mean, it would tell us that these eigenvalues are real. This is what it's telling us. Sorry? Yes, I mean, as I said, there is no way of having both a real partition function and a gauge invariant partition function. So we insist on gauge invariance because we want to gauge. So we give up the fact that is real, and we introduce a phase. We still want the property that, depending on the sign of the eigenvalue, we get plus or minus 1. And so we construct this regularized sum, or from product of the signs, but since it is a regularized version, is not equal to plus or minus 1. It's a sort of analytic continuation. Well, it is the analytic continuation of the regularized version. Yes. 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 Yes, the problem is that so this object is formal, is an infinite product, and is not convergent. So you have to do something with that. And I said, for the modulus, there is no problem for the absolute value. You can do, you could do, for instance, the sum over the eigenvalues at minus s, and if the real part of s is bigger than, 1, this convergence, you do analytic continuation, sorry, this. But you have a problem with the sign, if you insist that you want to get something which is real. Well, if you give that up and you admit that it can be some complex number, then you can get something which is gauge invariant. But once again, this object is not just plus or minus 1. Cannot be. It's some generic phase. Any other question? Okay, so this index theorem tells us this, that this particular exponential of the eta invariant can be written in terms of Chern-Simons terms. However, the combination that we have here is half of that, or if you want, is the square root of this, okay? I mean, there is 1/2 here, so it's the square root of this quantity, and so we might be tempted to say that, okay, the regularization of the fermion gives us half unit of Chern-Simons term, and this is almost correct. It's not precise, because it will mean that we have to take a square root of this expression, and then we are back to the same problem, that the square root is a sign which is not well defined, and then if we do this transformation, we get clashes with gauge invariance. But for most purposes, in particular if you do perturbative computations, this behaves like half a unit of Chern-Simons term. And so what we have described is the so-called parity anomaly. So the fact that, well, the theory is, so if you want, this is, in some sense, a Toft anomaly, in the sense that the theory is parity invariant, but when we turn on a background, the partition function is not possible to maintain this parity invariance. And since the effect that we obtain looks like half a unit of Chern-Simons term, we will use the following convention, that when we write down, so if you have a theory, a gauge theory with fermions, and this theory is some Chern-Simons theory, we indicate the effective Chern-Simons level, which is the bare Chern-Simons level plus this minus 1/2 for each fermion, which is the effect of the regularization of the fermions. And so in particular, if I want to discuss, so if you want to write down a theory which is a fermion coupled to a gauge field with no Chern-Simons term in the Lagrangian, we would indicate it like this. So a level minus 1/2. Okay, in our notation. So this would correspond to a theory in which we have, for instance, this fermion coupled to a dynamical gauge field, but there is no Chern-Simons term in the Lagrangian. Yes, let me just make one comment. So you might say, okay, I cannot, so we discussed at length that we cannot, I mean, Chern-Simons at a level which is not integer is not well defined. And you might say, okay, now we have some expression which is gauge invariant. And since it is gauge invariant, I can put any fraction that I want here. So can we actually use this eta to construct generic actions in which we have actually a real, what we could interpret as a real Chern-Simons level? And the answer is no. Because it is true that this object is gauge invariant, but it has another problem that is not continuous. And in particular, this regularized expression has the property that when some eigenvalue goes from negative to positive, this function jumps. So if you wish, this function is not defined when there is a Fermion zero mode on the manifold, and it jumps by 2. It jumps by 2 when this eigenvalue goes from negative to positive. In fact, this corresponds precisely to the fact that this exponential changes sign, so this is correct. And so if we try to put this object into the path integral, it's like putting an action which is not continuous, so this is bad. And in fact, this object, if you wish, only makes sense in conjunction with this absolute value of the partition function of a massless fermion, because precisely at this point, okay, maybe this is continuous, but in any case, this is a 0. And so the whole thing remains continuous. But if you just try to put this into the Lagrangian, in the action, in the path integral, it would not be continuous. Okay. And then, now we could ask, okay, what happens if we turn on a mass for this free fermion? So we turn on a mass term, and we take this mass term to be very large, and we can understand what happens, for instance, if you do Pauli-Villars regularization. What happens is that we obtain two different things, so two different limits of this object, depending on the sign of the mass. So if the mass is positive and very large, essentially these two phases that were either I or minus I, in the limit in which the mass goes to infinity, they go to 0. And so this phase goes away, and so z goes to 1. But if you take negative mass, these two phases go to -1, and which means that essentially instead of taking half of this eta, you have the whole thing, the whole eta, but the whole eta is equal to this object here. And so in that case, you get something non-trivial. You get, well, your partition function goes to e to the minus I pi eta a g, which you can write in terms of Chern-Simons. And in fact, I mean, in terms of the effective action and low energies, this is the same as minus, so a Chern-Simons term at level -1, and then this gravitational Chern-Simons term. Okay? Now, of course, this separation between positive and negative somehow depends on the regularization. One could have used the regularization in which you put a plus here, and but I mean everything would have been the same up to adding local counterterms. So of course there is some choice of regularization here, some choice of counterterms. You would have gotten the same. Okay, questions? Yes.
I'm a bit lost on this. What happens when you change the mass?
Yes. So one way to see that. So if you do Pauli-Villars, so Pauli-Villars means essentially that you introduce a field which is bosonic. So it has bosonic statistics, but it has the same Lagrangian. And so when you compute the partition function, instead of getting the determinant in the numerator, you get in the denominator. And so you get something like product of the eigenvalues, where you have, here you have the eigenvalues, and below you get eigenvalues, let's say, minus I lambda, okay? And now of this thing, we only look at the argument, because we say that for the absolute value, there is no problem. And so that result comes if you take lambda to, or maybe my regularization here have a plus. If you take lambda to plus infinity, then the argument goes to minus I, which is what this thing gives. And if lambda is negative, you get minus I. Sorry, you get plus I. And then when you introduce the mass, you go to argument of product, and here you have lambda k plus IM. And now you take M to be very large, but is essentially the same order as lambda. And so what happens is that if the mass, okay, my regularization lambda is positive. So if the mass is positive, from here I get just, the argument is 0, so it's just 1. But if M is negative, I get minus 1 for each of them. But then I have to regularize this infinite product of minus 1, which gives me the eta invariant. Okay. Yes, we are just rephrasing a standard one-loop computation, this one-loop shift of the Chern-Simons level in this language. But it's a one-loop computation that we are doing. Okay. So now we understand fermions. I would like to, so yesterday we presented this bosonization duality. And so we said, so let's see, so we said, so U1 level 1 with a scalar. In fact, the claim of the duality, so the conjecture duality, was that in the infrared is just a free fermion. Okay? So this was the claim. So in particular that we can bosonize a free fermion in terms of this Chern-Simons theory. This is essentially three-dimensional bosonization. And let me write, as we did yesterday, this in Lagrangian terms. In particular, I would like to keep track of the coupling to a background, in particular to a U1 background, and keep track of the counter terms for this background. So this theory, so there is a U1 which is dynamical, and there is a Chern-Simons term at level 1, and then the coupling to the background, since it is a coupling to the magnetic symmetry, is through this mixed Chern-Simons term. And on the other side, we have just the free fermion coupled to the background. By the way, as a further check of the duality, you can try to turn on mass terms on both sides, either positive or negative. You can do this exercise of integrating out, but you can do it keeping track of counter terms for the background, so both for B and for the matrix of this Chern-Simons gravitational term, and you can check that all the counter terms work out, okay? These counter terms from background fields, those are observables, and so the duality should reproduce them, and you can do as an exercise, you can check that they match. Yeah, I'm sorry, I'm not writing the wedge, just to be faster. So when I write ADA, I mean a wedge DA. Also here there is a wedge. Okay, so now we can take this duality and we can use a gauging procedure to derive a new duality. So how do we do that? So first of all, we can freely add local contour terms for background fields, okay? As long as we do it on both sides in the same way, this still remains a true duality or equality of the partition function at long distances. So in particular, let me add L over 4 pi b dB and L over 4 pi b dB for some integer L. Then let me introduce a new background field which is coupled magnetically to this B. So let me add 1 over 2 pi b dc. I'm just using minus arbitrarily. Okay, these are all background fields. So since they are background, they are not path integrated. I can add them on both sides. They go in and out of the path integral sign in the path integral. But then we do something interesting and non-trivial. So now we make this B dynamical. Okay, so we path integrate. And so B, that was a background field, we promote it to a dynamical field, so I use a small letter. And then we do path integral, so we integrate over it. And, well, if we had an equality of partition functions for any value of B, then we integrate, we should still have an equality of partition functions, okay? Now, there is a small subtlety here because really this is an infinite duality, so one should, one could worry that whether it is possible to take a limit in which we are really doing this at long distances. So what we do, so this is the bare Lagrangian, and in the bare Lagrangian, Chern-Simons term always have to be integer, because if they are integer, they are well defined. Then, in the full path integral, if we try to integrate out the fermions, then we will generate all these shifts that come from the regularization. But there is no problem here when I write, so to the Lagrangian I can add my terms, and I have to be careful that they are integer. I don't have to worry about the shifts. The shift will come out at the end when we do the regularization.
So don't worry.
I mean, we have to worry, but the worry is that all the terms that we write in Lagrangian should have an integer coefficient.
No,
that is the correct thing to do.
I was worrying about the free Fermion. What we said before is that the free Fermion.
Exactly. So we will do a regularization, which is gauge invariant, but which will generate an effective half unit of Chern-Simons term, which is effective. It's not half unit of Chern-Simons term in the Lagrangian. There will never be half unit of Chern-Simons term in the Lagrangian. So this is very important because if you start putting this 1/2 in the Lagrangian, you might make mistakes if you're not careful. While if you use this procedure in the Lagrangian, you only put integers, well, it's safe. Now, of course, as long as you do things carefully, of course, you're going to obtain correct results either way. Okay, so we do this procedure, and then we should have a new duality. So let me try the case L equal to 0. Okay, it's just a choice. So, okay, so first of all, let's remove this, and then B will become dynamical. And now this case is particularly nice and simple because now you see that B only appears linearly in this Lagrangian, and so essentially it is a Lagrange multiplier. And what it does, so the B, what it does, it sets A equal to C. There's a delta function on A equal to C. And so what we get on this side, let me write it here. And so what we get, so on that side we find dc phi minus phi to the 4. Yes, plus 1 over 4 pi c dc. And on the other side, we find I psi bar. On the other side, instead, okay, B becomes dynamical and remains dynamical. Okay. And so what is this? It's a new duality. So let's read off what this is. So here, this C is capital, is background. So there are no gauge fields here. There is just phi. So this is the O2 model. And we always assume that we tune in such a way we go to the fixed point. So this is the O2 Wilson-Fisher fixed point. And this one here, instead, there is a fermion coupled to a gauge field. So it is a U1. There is no Chern-Simons term in the Lagrangian, but there is this minus 1/2 shift. So this is level minus 1/2 with psi. And okay, it is coupled to its background for the U1. Okay? And so what we have found is a new duality, which we can call now fermionization duality. Which is telling us that, well, if you take this gauge theory, which is as close as we can get to QED with a single fermion, in the sense that level 0 does not exist, so level minus 1/2 or plus 1/2 is as close as we can get to 0. In fact, in its space diagram has a second order phase transition, which is described once again by the Wilson-Fisher fixed point. Yeah, so as I said yesterday, I'm not writing the Young-Mills term, but it's always there. So when they are at level 0, of course, it must be there. But even when it is a Chern-Simons theory, I'm regularizing the theory with some Young-Mills term. So I'm always assuming that there is also the Young-Mills term. Yeah, it's in the infrared that it gives you a delta. So you have to go. So if you want, you have to take a limit in which the scale of the gauge interactions is very high. And as I said, it's not completely obvious that this is going to work, right? Because if this was an exact duality, of course the partition function is exactly equal, and then if you part integrate over the source, you're going to get the same. This is an infrared duality. And so you might worry that, I mean, you have to think whether you can take a limit in which dominant contribution really comes from long distances. Yes, yes. Sorry? I'm sorry, I didn't understand.
Are you assuming anything about the background?
So C is a background, is a U1 background gauge field, which here it was coupled to B in this way with this mixed Chern-Simons term. Okay, now we make B dynamical, and since it is linear, it acts as a Lagrange multiplier. So it localizes the path integral to configurations in which this dynamical field is equal to the background that we turn on. Okay? If this C was 0, it would freeze this gauge field to 0 up to gauge transformations. But for a generic background, it freezes it to the value of this. Okay? And then, if you want integral over B, give you a delta, and then the integral over A just removes A and the delta, setting A equal to C. And this is why here I've put C, and here I've put C. Okay. So the question was if there are flat connect. So if really this fixes A equal to C, or if there are residual modes that we should integrate over. Was this the question? So the statement is that if we have a theory in which, so we take this theory of this gauge field and we couple it. So we take a Lagrangian in which we have some gauge field, let's call it V, and the only coupling that we write is, so this is coupled to some, I mean, this can be some background field. And we perform this path integral. Let's see, is this leaving us flat connections? I believe it does not, but in order to give you a sharp answer, I need to think a moment about it. So the statement is that this, let's give you a delta function at b equal to 0 up to gauge transformations. Yes, but I need to think a moment about this. Okay, any other question? So the question is if this...
This question I just want to understand.
Yeah, so in this duality now, the only gauge field is the background one. So this is the O2 vector model. On this side, we have a fermion coupled to a dynamical gauge field, and the level is -1/2, and it is coupled still to its background for the magnetic symmetry. Yes, that is true. Yes, so yes. This is also dual to U1 level 0 with phi tilde. So, but in the theory without, so well, classical is marginal. If you do pure scalar theory, I believe it is marginally irrelevant. Now you could ask in the theory with gauge, and well, it's not obvious. It's well, I don't know exactly what happens in that case, and I'm not sure if anybody knows. Let's see, so, yeah, I mean, of course we can check the phases, and let's do that. So, okay, so if we have a negative mask here, then if the mass is negative, we integrate out the fermion, we get U1 level -1, which is a trivially gapped theory. But if we take positive mass, then we are left with U1 level 0, which is a free photon, and in particular this spontaneously breaks the magnetic symmetry. The order parameter is the monopole operator, or if you want, this is dual to the compact scalar. So this is S1 Goldstone boson. We do reproduce the physics of this. Of course, this is one check that we have to do. Yes, but this appears, yes, this appears as a free photon, which is dualizable into a compact scalar. No, so the theories in the UV are different. The claim is just about the behavior at the fixed point. And so in this sense, I was saying that here it's not completely obvious that this is justified in the sense that you really would like to first go to the CFT and then perform make B dynamical at the CFT point, okay? And so, but essentially the idea is that you want to, so when you make B dynamical, what you do, you introduce a dynamical Yang-Mills terms for it, and essentially, well, you have a scale that you can choose, and what you will do is you will choose this scale to be in the far infrared, where the two theories has become the CFT. So in that way, above that scale, this is essentially free, or is weakly coupled, and only becomes, only becomes, if you want, interacting interacting at a scale where now the two theories have already reached the CFT. So essentially, if you have the two theories, A and B, and the claim of the duality is that only in the infrared they go to the same CFT, then when you gauge this background field, then you have to choose some G squared, which is... Yes.
You derive this mu.
Yes. So that is the point, yes. Yes.
You have like two different.
Yes.
The original and the one.
Yes.
And this one.
Yes.
So these two different dualities.
Yes.
They do not come from the same UV theory.
No. No. So this is a duality generating technique that I'm trying to describe here. In fact, you can generate an infinite number of dualities because I only described the case L equal to 0. And from the bosonization, I got this fermionization. I could choose any other L, and yes, and I'm not going to write all these dualities, but in fact it's an infinite number of dualities. In some sense, they are not independent, in the sense that from these you can get to the other ones. And it turns out that so for instance, from here we still have this background C, and so we can repeat the trick here. So now we could add a counter term for C on both sides, couple C to D, and then make C dynamical. You get a new infinite family. And one of these theories in this family will correspond to going back. And, well, essentially there is one infinite family. And this procedure allows you to move among them. So they're not independent. From one, you can derive all the other ones. In fact, it turns out that you can start from the bosonization duality. You play these tricks, you generate all these infinite families, and you can use it to derive the particle vortex. Derive up to this subtlety of the scales. So you could start from the bosonization and derive the particle vortex. Okay. Okay, so now, in these 10 minutes, so I'd like to describe the fact that, in fact, there exist, so these simple abelian dualities that we have discussed admit vast non-abelian generalizations. And the origin of these generalizations is, well, if you want, dates back to a work of Igor with Polyakov, where so they were proposing that vector models, so models in which, well, vector models that Igor discussed in full details, in 3 dimensions. In the large N, they proposed are dual to so vector models with either scalars or fermions. They propose are dual to some higher spin gravity theories. Of Vasiliev. And the motivation for that was that, well, if you take large N, these vector models, at the leading order you have higher spin currents, which are conserved. And so they should be dual to a theory in which in the bulk you have gauge fields of all the spins. And, well, later, people understood that, in fact, one could generalize this duality. In fact, these were higher spin theories in ADS4, because these were vector models in 3D. Then people understood that it was possible to generalize this duality to the case in which you actually gauge this vector model with Chern-Simons interactions. Say some UN level K, and one has to take a top limit in which N goes to infinity, but also K goes to infinity, and what is kept fixed is the top coupling N over K. Well, in this duality, the vector models could contain either scalars or fermions, but in fact, in this generalization, it turned out that both the model constructed with the scalars and the model constructed with the fermions were due to the very same higher spin gravity theory of Vasiliev, and so this was implying or suggesting that the 2 theories should be dual, okay? So, well, because of lack of time, I will not go through the historical development of this story. So I will not describe the large N. I will just say something maybe tomorrow. But in fact, I will jump to the finite N proposal for this duality. In particular, I will not talk about gravity or ADS-CFT. I will just describe what is the proposal for these field theory dualities at finite N. And so, well, there are various proposals. So one of them is the following. So SUN level K with NF scalars is dual, as in the infrared, to UK minus N plus NF over 2 with NF fermions. So as you see, it's similar to the previous ones. Now we have gauge fields on both sides. On one side there are scalars. On the other side there are fermions. And as before, on the fermionic side, the only interactions are gauge interactions. But here there are quartic scalar interactions. And in particular, well, it turns out that if you take these non-abelian theories, and you insist on preserving the maximal possible symmetries, there are 2 types of quartic interactions that you can turn on, which essentially is what Igor already described. So you can have an interaction if our field has some gauge indices and some flavor indices. There is a single trace interaction that you can write. So IA, IJ, and then BI, BJ. And then there is a double trace interaction, which is AI squared. So in general, both these interactions will be present with some coefficients that will renormalize to a suitable value in the infrared. And then there is another version which is similar. Instead of having SU U, it has U SU. Okay, in fact, it turns out that there are more versions of this. For instance, well, there is a version in which you have unitary group on both sides, but somehow the level for the SU part and the level for U1 is different. This is something that you can do in UN. There are versions where you have symplectic groups. There's a version where you have orthogonal groups. Okay, any question? And a small piece of the operator map is the same, is similar to what we had before. So the mass operator on one side is mapped to the mass operator up to a minus sign on the other side. Okay, so I have a few minutes, so I would like to mention a few checks that one can do about this proposal. So first of all, we can try to take special cases. So one special case is to take n equal k equal nf equal to 1. So let's take them very small. And if we do that, so SU1 is not a gauge group. So here there is no gauge. We have just the scalar. And here we have U1 level minus a half with a fermion. So for instance, the first one gives us O2 Wilson-Fisher dual to U1 minus a half with the fermion. And this is precisely the Fermionization duality that we just described. So it matches with what described before. The second one, now here we have U1 level 1 with the scalar. And here the gauge group disappears. We only have the fermion. And so we find U1 level 1 with the scalar dual to a free fermion. And once again, this is the bosonization duality that we discussed before. This also nicely matches. And moreover, as we described, you can take these two, you can play with them, and you can, quotation mark, derive particle vortex. In fact, it turns out that even these two dualities are not independent, because you could play this gauging game also on this theory, so you could couple them to a background field for a U1 symmetry, and then repeating this game of gauging, one could go from here to an infinite number of other ones, including this one. Some other nice checks that one can do. For instance, you could try to give mass. You could try to give mass to one of these flavors. And of course, you could choose positive mass or negative mass. And essentially what happens is that on the fermionic side, if you give mass to one of these flavors, you're going to shift the Chern-Simons level by 1 unit, either +1 or -1 unit. When you do it on the scalar side, well, if it is a positive mass squared, you're going to lose a flavor, but nothing changes in the gauge group. If it is a negative mass, you have condensation, but since it is a single flavor that condenses, it's going to break the gauge group by 1 unit. And so somehow you reproduce the same duality where either the rank of this side or the level on this side is shifted by 1 unit in some direction, and one can check that it's precisely consistent with the duality just by changing this parameterization. So it reproduces itself but with different numbers. And okay, so I will probably stop here. I will mention some other checks that one can do tomorrow. And in particular, a nice check on which I will spend some time is Toft anomaly matching. Which is particularly nice because there is no chiral anomaly in these theories, and so we'll talk about some other type of anomaly, which is not the standard chiral anomaly. Okay.